Okay, so hello everyone. I'm Gianluigi Silvestri, and I'm at the second year of my PhD at the One Planet Research Center. One Planet Research Center is a joint group, let's say, between IMEC. IMEC is a Belgian company in nanoelectronics that has also it's also in the Netherlands, and so it's collaboration between IMEC and some local universities, including Radboud University, which is the university that I'm in, and the Donders Center at Radboud University. And my research is about variational inference, normalizing flows, and reinforcement learning. And this work is a bit at the intersection between variational inference and normalizing flow. And during the talk, I will cover our latest preprint that is called Embedded Model Flows, combining the inductive biases of model-free deep learning and explicit probabilistic modeling. Do you all see my pointer? Yeah, maybe like this is better. Okay, so what I will talk about during the presentation is first a bit of a description between the differences of generative models and probabilistic programming and the strengths of each paradigm, and how we try to combine them with the embedded model flows. So this is just a representation of what an embedded model flow is, and later we will see what all these components mean. Before diving into the actual contribution of the paper, I will cover the normalizing flows, which are an important building block for this work. And then finally, I will describe the embedded model flows, and I will show some results in different problems for density estimation and variational inference. All right, so let's start with talking about generative models. We can summarize the goal of generative models with the task of learning an underlying distribution of some data points. So here we see some data points coming from a true underlying distribution, and our generative models want to learn the underlying distribution, possibly in a very accurate way, so that then we can do tasks with this distribution. For example, sampling new data points that look like the real ones, or in some cases when it's available, also doing density estimation. So given a data point, telling us what's the probability of the data point. So in literature, perhaps the two most common examples of generative models are generative adversarial networks, in which you have this discriminator network and generator network, and the generator has to generate realistic looking images to fool the discriminator, while the discriminator has to recognize which images are real and which are fake. Or we also have variational autoencoders, in which an encoder learns latent variables, so learns to embed the input into a latent space, and then the decoder will sample from this latent space and reconstruct real-looking images, and this is trained by maximizing the evidence lower bound. Both these models can only sample from the learned distribution, and we will see later that with normalizing flows we can also do density estimation with that. So when you design a generative model, the principle is to make them as flexible as possible so that they can learn any sort of complex data distribution. So these tools are usually very generic, but they lack the possibility to, for example, introduce specific knowledge, specific prior knowledge that the user might have. And on the other hand, we have probabilistic programming, and probabilistic programming is can be summarized as a tool to combine prior knowledge and data, so data-driven knowledge to make predictions. So you can train your probabilistic programming models by maximum likelihood or Bayesian inference, and usually the way in which prior knowledge is specified is by using directed acyclic graphs or Bayesian networks. So you can you can specify your understanding about latent variables and observable variables with graphical models. And there are cases in which we have a strong understanding of the systems that you're trying to model. For example, in physics or in dynamical systems, we have a good understanding of the evolution of these systems with stochastic differential equations, and these laws can be easily embedded with a graphical model. However, we have Box said that all models are wrong, but some are useful. So this is a quote from George Box. He was a statistician, and he's famous for his work on time series analysis. He created the filters autoregressive and ARIMA and ARMA. And so basically what this means that even if we have a very good understanding of what we are modeling, there will always be some imperfection, either due to our understanding of what we're trying to model, or because of assumptions that we make so that we can use the models, for example, some independence among variables. So what we try to do in this work is to bridge the gap between deep generative models and probabilistic programming. So having models that are flexible and capable of modeling pretty much any distribution like generative models, but also a way to add our prior knowledge into these models so that we can make use of what we already know of the problem that we're trying to solve. And we do this with the embedded model flows. Okay, so before talking about the embedded model flows, I will now explain what normalizing flows are. And please, if you have questions or comments at any time, feel free to interrupt. Okay, so normalizing flows are generative models, can be somehow compared to GANs or variational encoders, and they work by a sequence of invertible transformations. So you will have a base distribution Z, and you can map this distribution to any other distribution by a sequence of these invertible transformations. Since these transformations are invertible, you can do the transformation also in the opposite direction. So you can start from the data and map it to the base distribution and then find the probability of this data. This is just a schematic representation for a 1D variable in which you sample from a base distribution, and usually the base distribution is a spherical Gaussian, and through a sequence of these transformations, you map it to a more complex distribution, which is the distribution of our data. And you can do also in the reverse. So from the data, you can map it back to a spherical Gaussian. And now we will see exactly how this works. So in normalizing flows, you have to specify this base distribution with a known density function P of Z. So it's almost always spherical Gaussian and can be, of course, multidimensional. So if it's if it has more than one dimension, usually it's all independent Gaussian variables, and then you can transform these samples from the base distribution with a one-to-one invertible mapping. So you would obtain X, which is the function f of Z, in this case in the forward direction, and then you can obtain Z by doing f minus 1 of X. So again, you sample Z from the base distribution and you obtain X by applying the function f, and you can reobtain Z by doing the inverse. And this is a one-to-one mapping between Z and X. How do we compute the probability of X? We use the change of variable formula. So if you want to know the probability of X, you can find the probability of the base distribution of Z after transforming, of course, X with f minus 1. And then you have to multiply by the determinant of the Jacobian of f to account for the change of volume induced by the transformation. If we were limited to one only invertible transformation that could be perhaps not have enough capacity. So what you can do in normalizing flows is to combine several invertible transformations to have a more flexible model. And then you can still compute the probability of the data X, or in this case, the log probability, by computing the log probability of the base distribution, so of the variable mapped back to the space of the base distribution, minus the sum of the logarithm of the absolute value of the determinant of all the sequence of transformations. What happens in practice is that you can't really use any invertible function. There are some constraints. So these transformations have to be computationally efficient. They have to be easy to invert, but most importantly, the computation of the determinant of the Jacobian has to be efficient. So we show now a couple of examples. This is real MVP. It's one of the most popular normalizing flow models. And in each transformation, the base variables are split in two groups. And one is the identity, while the other group is transformed with a scale and a shift function, which is function of the first group. So these are called coupling layers. And the Jacobian matrix would be triangular. So it's efficient to compute the Jacobian because it's just a sum of the the determinant of the Jacobian is efficient because it's the sum of the elements on the diagonal of the Jacobian. And the inverse can be done with the same complexity of the forward because you just subtract and divide by the same parameters, while the first group is still going to be the identity. And in real MVP, you usually stack several of these transformations in which first you transform one subset of variables and the other one is the identity, and then you invert them. So then you transform the first group of variables and you keep the identity of the second. Another popular flow architecture is the master regressive flow. So the limit of real MVP is that you do little coupling among variables because first you basically transform one group and then the other. In master regressive flow, you apply an autoregressive transformation of all the variables. So each variable is transformed with this Gaussian emission, which is function of all the previous values in the inputs. So the Jacobian, the determinant of the Jacobian is still very efficient because the Jacobian, given the autoregressive transformations, will be triangular. So the determinant of the Jacobian will be still the sum of the elements on the main diagonal. The downside, let's say, of master regressive flow is that they are slow in one direction. So in this case, there will be slow in the sampling direction because for each variable you have to do the forward pass of the network to get these parameters, and this forward pass will be conditioned on all the previous inputs, while the inverse is going to be efficient because you already have all the transformed variables and you can just do one reverse, so one forward pass to then do the inverse of this formula. Perhaps I didn't mention it earlier, but you can train normalizing flows in both directions. So you can train them by mapping the inputs to the base variables to do density estimation. So in that case, you just want to maximize the log probability, and you can train them also in the opposite direction. So by sampling from the base distribution and mapping these variables to the data space, in case, for example, you have available the distribution of the data, and that's done, for example, in variational inference, in which you want to use normalizing flows to train approximate posterior distribution. So you sample from the base distribution and transform the variables to match the posterior distribution of the variational inference problem. So in that case, so master regressive flows are commonly used for density estimation. If you want to, because they're fast in the training direction. If you want to use this architecture for variational inference, it's usually used inverse. So it's called inverse regressive flow, and it's simply a master regressive flow, but in the reverse direction, so that the sampling direction is going to be faster. Okay, so just to wrap up this part, we saw what normalizing flows are, and are this sequence. Oh, there is a question. Okay, I will speed up a bit. So basically, yeah, normalizing flows are are this sequence of invertible transformations that have to be computationally efficient, easy to invert, and efficient to compute the determinant of the Jacobian. And now we will see how we use this in the embedded model flows. So what we want to do is to use normalizing flows and also add probabilistic programs to add a structure. And these probabilistic programs, we want to use them as a layer of normalizing flow, so that they have to be invertible, and the Jacobian of these layers has to be computationally efficient. So we want to basically map a full graphical model into a normalizing flow layer. So that in a one-dimensional case, imagine we have our probabilistic program is a mixture of Gaussian, then we want to find a way to map a spherical Gaussian into this mixture of Gaussian with an invertible transformation. And we do this by using the probability integral transformation. So the probability integral transform theorem says that if we have samples from a continuous distribution and we apply the CDF function, these samples will be mapped to a uniform distribution. So in this case, we see a Gaussian, we sample from the Gaussian, we apply the CDF, and the result will follow a uniform distribution. So yeah, if we take if the CDF is invertible, we can then sample from uniform distribution and apply the inverse CDF, and that will give us samples from the original distribution. So yeah, this is what I just said. So if we want to start from a spherical Gaussian, we can sample. We can take samples from the spherical Gaussian, apply the inverse. No, never mind. Sorry. Apply the spherical Gaussian CDF, and then apply the inverse CDF of any distribution to get samples from that distribution. So I will say this again. Sorry, maybe it wasn't clear. So we have a continuous distribution of any kind. We know that if we have samples from a uniform distribution and we apply the inverse CDF of that distribution, we obtain samples from that distribution. So if we want to start from a spherical Gaussian instead of a uniform distribution, we can sample from the spherical Gaussian, apply the forward CDF to map these samples to a uniform distribution, and then apply an inverse CDF of our base distribution to obtain samples from that distribution. So this is just an example. We have the samples from the spherical Gaussian, forward CDF, uniform distribution, and then here we have a mixture of Gaussian. We apply the inverse CDF of the mixture of Gaussian, and we obtain samples from this mixture of Gaussians, basically from a spherical Gaussian. And just an example with the Gaussian variables. So here we have a generic Gaussian, and the inverse CDF of a generic Gaussian is the mean plus standard deviation times the inverse spherical Gaussian from a uniform distribution. And this assumes that we start from a uniform distribution. If we want to start, as we saw earlier, from a spherical Gaussian, then we do forward CDF of spherical Gaussian, which cancels out with this term. And so basically we obtain that samples from our Gaussian distribution parameterized by mu and sigma, can be obtained by mu plus sigma epsilon, and epsilon is our base spherical Gaussian. And this is the reparameterization trick that is commonly used in variational autoencoders. And the inverse of this formula is x minus mu divided by sigma. So we have found a way now to transform samples from a spherical Gaussian to any distribution which has a which has an invertible CDF. And the logarithm of this transformation is just log of sigma. So how do we, now we just saw how we convert one univariate random variable to an invertible bijective transformation. Now I'm going to show how we can do this with graphical models. So this is just an example of a graphical model, and we write this probability as the joint probability of all these components, in which each variable is parameterized by the parent variable. So for example, x1 will depend on the samples from x0 and so on. The way we can do this is to transform, to map into a bijective transformation each variable of this graphical model by taking into account the parentage structure. So x0 will be just a simple transformation, while x1 will have to be transformed, taking into account also the transformations of all the previous variables in the graph. And the inverse transformations can be done in parallel because we already have all the variables as an input, and this is similar to what we saw earlier in the masked autoregressive flow. So since we are transforming a direct acyclic graph, the relationship among variables will be autoregressive, and the Jacobian of this transformation induced by autoregressive graphical model will have a triangular Jacobian. So the Jacobian matrix, the determinant of the Jacobian will be easy to compute, as is the sum of the components on the diagonal of this Jacobian matrix. And here I just show a 2D example. We want to map the spherical Gaussian into the Niels funnel distribution that is specified by two variables, z plotted on the y-axis and x plotted on the x-axis. So first we sample z and then x depending on z. So you can first do the transformation of z, and then based on what you sample, you can do the transformation of x. And we can map the spherical Gaussian to this more complex distribution with a one-to-one invertible mapping. But as we mentioned earlier, all models are wrong. So we add a gating mechanism so that if we may specify part of the model, that can be canceled out. So instead of having our bijective transformation f, as we showed earlier, we add gates and we create a function g. So we will use lambda is our gates, and we will have one gating parameter for each variable of the graphical model, and the lambda will be bounded between 0 and 1, and will perform a convex combination between f and the base variable, so the identity. In the case of Gaussian, this becomes the forward transformation, and we will also have so we can have both forward and inverse transformation, and the inverse transformation with the gates. I think the gates will also help improving stability in the reverse transformation. So this is basically a mechanism in which we can specify a model, and with the gates, again, we can correct it if it's misspecified. This is the algorithm of a forward sampling with the gated functions. So for each variable in our graphical model, we find the parents of the variable, and then we construct the forward transformation given the parent variables, and then apply the gates and compute the log determinant of the Jacobian. Here I show for different values of the gates how like we can see visually how that interpolates between the base distribution and the distribution from the graphical model. And in these plots, I use the same gates for both X and Z, even though, again, in the algorithm, there will be one gate for each variable. Okay, so now that we have covered this mechanism of transforming graphical models into invertible transformations, here we see an example of what an embedded model flow is. So we start with a base distribution, and then we apply normalizing flow layers, so that are generic, basically. So generic normalizing flow layers, and then our gated structure layer. And what this does is that the normalizing flow can learn the deviation from the specified model. So the flow can correct our model, plus the gates that can rule out part of our model, and yeah, to basically learn the target distribution. So what we do is to combine the flexibility of flows plus our inductive biases, and the flow can correct these models. And we will see later how this helps learning for the whole flow. This is just a code snippet of how we can simply implement this in an automatic way in TensorFlow. So we specify a structure, in this case is a continuity structure, in which each variable will be centered on the previous variable plus some noise. And once we specify the structure with a joint distribution coroutine, then we can just define a base normalizing flow, embed the structure with this class gated out from normal, and then combine the two to have our resulting embedded model flow. I didn't mention here, but in this example, we just place one gated structure layer on top, but in principle, there is no real limitation. So you can place more of these layers in the whole model, or perhaps alternate a flow and a structure layer, and then maybe another flow and another structure layer of different structures and so on. Okay, now it's time for showing some applications. Is there a question? Okay, maybe now it's a good, okay, no, when it's, okay, we'll wait for the next 2 minutes and then join the new room. So some applications and experiments. The first structure that we try to embed is multimodality. So we embed an independent mixture of Gaussian distribution for each variable of the model. And we use it to train the model in the density estimation direction, so from the data to the base distribution. And so we use the inverse transformation during training, which is the inverse, simply the inverse normal CDF of the CDF of a mixture of Gaussians. And here is what basically happens. Our forward CDF of mixture of Gaussian maps mixture of Gaussian to this uniform distribution, and then again to spherical Gaussian. So this works well with training, but for sampling, then we don't have a closed form solution of the forward transformation. So we have to use root finding methods, which are a bit slower, but they're still very easy to use, especially in TensorFlow. There is this function that allows you to do that automatically. And here we see some results. We train the models on 2D toy models, 8 Gaussians and the checkerboard, and also on MNIST. And we use as baselines master regressive flow, a master regressive flow with more layers, so it's a more complex, to show that having a more complex flow doesn't improve over simple flow with our embedded, with our structure layers. And then we add the structure layer with the multimodality on top of the flow and in the middle to see how it differs. And we see for the simple cases how having the structure bijective on top improves over master regressive flow. But then we also tried to use the neural spline flows, which are flows designed to handle multimodality and performs better than master regressive flow, but combining our structure bijector with neural spline flows still improves over the simple plain architecture. I'll just show maybe some visual results before changing room. And here is the ground truth, and here are samples generated or the density learned by the different models. So we see how the ones with the neural spline flow baselines are the best, but combining them with our structure bijector still does better than the simple baseline. Yes, so we saw the first experiments with the multimodality structure, and then we also try to use the structure layer on time series problems. In time series data, you have usually strong local correlations, so it's fair to assume that in some cases, or in most cases, it's fair to assume that each variable will be somewhat close to the previous value. So we had a structure, a discretized stochastic differential equation, which is the binary process. So when it's discretized, you can basically write it as a graphical model in which each value is Gaussian, as a Gaussian distribution around the previous value, and with some sort of standard deviation. And this becomes the bijective transformation xt, so the previous value plus sigma xt plus 1, and xt plus 1 is the output of the flow. So this is what we call the continuity structure, and we tried it in several toy time series models. One is a Brownian motion, one is a Ornest-Uhlenbeck process, one is a Lorentz system, and a Van der Pol oscillator. And we use the same baselines as earlier. We also add a bottom math. So in this case, we have a base distribution, and then immediately the continuity bijector, and then the maximal regressive flow. And in this case, we see how the best results are obtained by the gated embedded model flow with continuity structure on the top in all the models, and yeah, beating all the other baselines. And here we see some samples from the different models on the Lorentz system. So the Lorentz system follows these dynamics, and when it's discretized, the data is generated with this equation. So here we see plots or samples for the x coordinate. This is the ground truth, and the best quality results are obtained when sampling with the gated embedded model flow with continuity on top. And finally, we show how we can use this for variational inference. So a very quick introduction on variational inference. What we want to do is to estimate a probability of latent variables of our model given the observed data, and we can do this with the Bayes rule, but the evidence here is often intractable. So we use variational inference, so a new distribution QZ to approximate the two posterior distribution P of Z given X by maximizing the Kullback-Leibler divergence. So if this is the true posterior and we choose a good approximate distribution Q, then we obtain a nice approximation. If the approximate or the variational distribution is not flexible enough, and the true posterior is, for example, multimodal, then we get this poor approximation. So there have been many ways to solve this problem, and someone has tried to use normalizing flows to find the right posterior distribution, given that they can approximate any distribution. And this is a picture taken from the inversely regressive flow paper, in which the flows are used as a posterior in a variational autoencoder, and we see how the posterior learned with the inversely regressive flow is much better than the one in standard VAEs. But we have the same problem as, not the same problem, but the same limitation as before. So these flows are generic, but they don't reuse any prior information. And this is something that we have explored in previous work, in which basically the posterior approximation is usually a deviation from the prior. So we proposed techniques to embed the prior structure into the posterior approximation, and one of these works was published by Luca. Is the automatic structure variational inference, and the mean field approximation is enhanced by using also the variables of the prior. So you will still have the convex update between the variables of the prior and learnable parameters. So this worked very well for structure variational inference problems, but has the limitation that the posterior will be in the same form of the prior, and it cannot model dependencies that are not already in the prior. And then a follow-up of that work was cascading flows. So instead of using this sort of enhanced mean field approximation, each variable of the prior was transformed with a normalizing flow with gating mechanism. And then, so this improved over structure variational inference, but wasn't still perfect in modeling dependencies that were not in the prior, like collider dependencies. And here is how we can use embedded model flows for variational inference. So what we do is to use a inversal regressive flow and then embed the prior program as a structured layer. And then we train this by maximizing the evidence lower bound. And this is our representation of the samples after the inversal regressive flow and after the structured bijector. And these are distributions learned at a given time point. So here we took a middle time point, so at time step 14 in a time series of 30 time steps or something. And it's easy to see how using the structured bijector simplifies the job for the flow layer, which without the structured bijector would have to learn this complex distribution and this complex posterior, while with the embedded model flows, it only has to learn a deviation from the base distribution. So we show here some results in structure variational inference, and for each of these models, again, in the embedded model flow, we embed the prior as a structure layer, and we improve over baselines, including ASVI that I described earlier and inversal regressive flow. We improve on these time series problems in which, especially for the Lorentz system and the Van der Pol oscillation, there is a strong structure. So embedding the prior, of course, is an advantage, especially compared if we compare the results with the generic inversal regressive flow. But also we improve in hierarchical models, especially these last two are Gaussian trees, Gaussian binary trees, in which the prior cannot model the collider dependencies. And so we see how the underlying flow learns how to model those dependencies, and that improves over other models thanks to the structure embedded with the prior. Here are just some plots of the learned posterior distribution. This is still for the Lorentz system, and the black line is the ground truth. The dots are the observations, and the orange line is are samples from the posterior distribution. And it's pretty much obvious how the embedded model flow outperforms the simple inverse autoregressive flow. Okay, so that was.
Maybe if I can add something, this is maybe slightly counterintuitive, but because theoretically a powerful enough flow can learn the prior, but in practice, if you try to learn the structure of the prior from the elbow from a generic normalizing flow is extremely difficult, and usually it simply will converge to the wrong local minimum. So it's the fact that the flow is flexible enough for actually doing the job doesn't mean that the job is usually done. And what you will see is that since it's trying to, that the elbow loss is often quite poor in giving you a good estimation of the prior. And therefore, if you don't embed the prior in the model directly, often you get completely wrong inference, as you can see here. Yeah.
Yeah, thank you. Okay, so some conclusions. Just to resume or summarize the contributions, we introduced embedded model flows, which can automatically convert differentiable probabilistic programs into bijective transformations. And by choosing appropriate inductive biases, embedded model flows can improve over generic normalizing flows. So this approach has some limitations. But the structured bijectors are still constrained to the topological constraints of the normalizing flows, which can be a problem in some cases. And there are works that study these constraints. This embedded, the structured bijector cannot embed latent variables. So for now, if there are latent variables in a probabilistic program, we have to treat them as observable variables. And we will, this can be improved, of course, in future works. If the structure bijector cannot be inverted, we have to use these root finding methods, which work well, but are much slower. So this, of course, can be a limitation in practice. We cannot model discrete random variables because then the structure bijector wouldn't be invertible and cannot propagate the gradients. And these directed acyclic graphs have autoregressive structures, which it's convenient in terms of Jacobian, but in some cases it can slow down the sampling, or especially in variational inference, the sampling can be slowed down if due to this autoregressive structure in the bijector. And now some future work. One thing that we haven't explored is the combination of different structure in the same embedded model flow, but there is no limitation to the structures that you can embed, and ideally this could help to model very complex dependencies in the data. And also we have used the structure bijector only in normalizing flows, but ideally one can use this transformation also in other architectures, for example, for classification and regression. And in that case, you wouldn't, or in some cases, you don't even need these transformations to be invertible. And finally, I would like to thank the people that collaborated in this project, Emily Fertig and Dave Moore, that are researchers at Google Research, and then my supervisor that is also here in the call, Luca Ambrogioni, that is assistant professor at the Dondersch Institute and Radboud University. Okay, so thank you all for attention, and now I think we have some time left for questions and comments.